Great. Welcome everybody to our first support workshop for our high altitude balloon mission with NASA Goddard. What I'd like to do is just recap the dates and deadlines. Then let's have a support Q&A session, and then let's have a look at the next steps. The plan was communicated. We had our onboarding workshops 2 weeks ago, and then we have our first workshops this week. 2 weeks from now, during the week of May 20th, we will have a second support workshop. And then from there, we need to make sure that all the payloads are built, that they're completed, that they're tested with you locally on site, and then sent off to us for integration, final tests. And then, yes, Jim, they're going to be all arriving at you. I know that we've had a little bit of email backwards and forwards in terms of the logistics and making your arrangements for your trip. So that's really all looking exciting. And yeah, the launch has been scheduled for August 12th. Sometimes that may move by a day or so, depending on the local conditions in New Mexico. And then, of course, everybody gets their payload back. Bridget, should we actually begin with you? If you just want to share, maybe you want to unmute the Q&A session that you had with Bianca during the week.
Oh, yeah, sure. So I was having a little bit of trouble with how to integrate the sensor I used on we're using on our payload. It's a SparkFun gas sensor, like BME 688. And so I had some questions about how to kind of make that connection, especially since on the prototyping board, which I hadn't used before. So just went over on a Zoom meeting, how to what wires to connect, and then I drew a picture and sent it back to him, and he confirmed that it's all good. So
okay, so that's great. And so that sensor, that particular sensor, so you're putting that onto one of the prototype boards. What data is that going to collect for you?
So that's gonna do a whole bunch of different things. I know we're still researching exactly what we want to get from the data, but I do know it collects sulfur gas in the air, which we could have a whole bunch of different applications for. And then it does environmental stuff. So yeah, and it does temperature and it does a lot, but the sulfur one's the main one that I remember.
So Judy, it's a buildup of the BME 680 that we used to use. So it has temperature, humidity, atmospheric pressure, and then it had volatile organic compounds, so CO2 equivalent. And then it has something that the 680 doesn't have, this 688, which is called gas scanning. So I don't know exactly what it is, but it sounds very interesting. So I have a feeling it's picking up a more detailed level of gas, and then kind of probably guess more what's in the gas than the 680 did. So it's very very interesting sensor.
Okay, great. And then Bridget, I was wondering, do you have anything there with the prototype board you can just show us?
Yeah,
on the camera?
it's right here.
Okay, great. Thanks.
I haven't had the chance to solder it on yet, but this is
okay.
Ooh, this is the sensor. Ooh, let's not drop it. But it's it's about the same size as the prototyping board. Actually, it's a little smaller, but so
great.
yeah, it's about the same size. And then what I'll do is line up the holes on the side of the SparkFun sensor with the single line here like that. And then,
Okay.
yeah.
Okay, great. That's perfect. Excellent.
So for the rest, so the board that was held up there was a prototype board similar to this one here. So this is green. There are also some whites in circulation here. So here's a white one, and here is a sensor connected to that board. So it's this kind of like wiring underneath here that's like a configuration that we had a discussion on last time. So this one is just another sensor from another company, but it's same principle. You simply solder it in, configure it here, and then, you know, most of the work lies in the software.
What group are you with, Brittany? Bridget, excuse me.
I'm with Mr. Gorman at Nipmuc.
Okay, thanks.
And do we have any other questions? Yeah, especially for Bianca and William and Jim. Jim more around logistics, I guess.
I can maybe just give an update on the CubeSat itself. So last time I demonstrated something that this one that Judy had in the picture. This is a new version, and it's going to be replaced by next week already. So it has this remove before flight that actually fits inside the casing. So there's simply just a remove before flight here. What this one also have is that it have a charging port. So this is a 4S charger. So this is kind of like a charger for charging for the batteries in CL. So instead of taking the batteries out, that can actually just be charged by plugging in this plug here in front of it. So there will be a little door in this thing here. I'm not printing a new one of that because the next prototype is actually on the way. Now, I've been working with 4 batteries so far, but the next version is actually only 3 batteries because I calculated that 3 batteries are fine. And I needed that more space. So one of the other things is that the reason why this is like this high is because the battery goes up into this space here. And it's a quite thick wall with this, you know, it's a PLA is like polystyrene. So, and this is 10% infill. So it's kind of like lock the air inside. So they all work as an insulation. So the battery is in here, and these screw holes is there's going to be a plate that comes up underneath that then insulate the battery from the outside. So what the battery module also have is a heater. So I have this little heater experiment I've been playing with here as my heater test here. So this is a little box that have a similar size wall. And this is actually the heater. It's a one big resistor. And then there's a MOSFET that turn it on and off and a control board. So this works with I2C. So this a unit here asking the temperature sensor, which sits there, what the temperature is, and then depending on what the temperature is, it turns it on or off. And the duty cycle, so I put this in a deep freezer here for -22 to see how it worked. And the duty cycle is around 8%. That means 8% of the time I have to turn the heat on. And it's typically I turn the heat on for like 20 seconds and then off for like 2 minutes or whatever that duty cycle matches. And I do that so it keeps the temperature at 0 degrees. So plus minus 0 degrees Celsius. Okay, so what's that? 32 Fahrenheit. So I just keep the temperature at that level. At that level, battery is fine. And I'm not trying to to drain the battery for heating it up more. So of course that means it's only once we get up to a certain altitude that the heater starts, and once it drops below a certain altitude and it's hot enough, and also when it's gone up to a higher altitude, it tends to kind of like not just be colder and colder, but change in depending on altitude. So the battery is actually not draining a lot just to heat this thing here. So this is my little heater box. So that's that heater, that was a prototype that's now implemented on the next version of this board here. There's also like a battery monitor that will tell me what the battery level is, and that's going to be stored on my own SD card. And then the side panels. So on this one here, let me just switch it off. Do that with plugging that one in. So the side panels, this is a site, which is meant to be, there's like now this 3D printed profile that clicks in. So there's these holes on a board. So it actually just clicks in. Well, that means it's each layer now are held in place by this thing here. And the idea is to remove the need for having these standoffs, because it just takes way too long time to put in, and especially if one have to replace something. So they're now just pure shelves. It holds back. And these screw holes, there's like a screw hole, 4 of them here, that screws into the container, so it's held together. So what's also updated on that is that each of the there was a problem is that this control board here gave power high when it started up. So I had to reverse the logic. So there's no power on the board when it starts up. And the reason for that is that each of the board, there is also a battery or a power sensor that measures each board's current and voltage. So if anybody exceeds the allowed current and voltage, then it will set out. And the whole thing is that that's getting measured, and then when Jim put it together, he will be able to connect to this thing here using his laptop or phone. It's just going to be a web page he log into, and it will give a status of everything. What's going to be ready, hopefully for the next workshop, is there's going to be a piece of software you can implement. So 4 lines of code you implement. So I'm making a library so you can implement it in Arduino. And that allows you to tell the host, the control board that sits here on the bottom here, what the status is of your board. So for example, when you start up and you go in and, for example, communicate with the BM680 date, you will get like a status whether it's working or not. If you have other things you do the same with, for example, maybe you connect the microphone and you kind of like just check if you get some sound, or whatever it is that you have, then at the end of your setup, you can then communicate back to the control module and say, what is the status? So you're going to have like very few characters to kind of like just give some flags. So when you see them yourself, you know if that means it's good or bad, okay? So that's all kind of like communicate over the CAN bus to the control module, which makes a web page, which allows us, when we integrate it, to figure out if things are working or not working. And there we will see for each layer what current do they draw. There's not really any guesswork with the voltage because I'm delivering that. But how much current they draw, we can see that for each level. And then there will be a status for each board that the programmer themselves can actually deliver. We're not going to necessarily lock down a lot here on this first mission. So the idea is that we can communicate, and as we kind of like go through the different steps, we'll be able to use this thing here also to figure out how we communicate when we eventually take the same thing and put it on the International Space Station. Because then there will be an ongoing communication using the CAN bus to the control module, then that then connects to NanoRac's onboard computer, and they have like connection to that, so we can download data that way. And that's all gonna use this thing here. So that's the reason why I've been working a lot on both the communication and the power for this thing here. The only thing that changes from the International Space Station and this thing, other than this rack here, is gonna be 2U high. So this thing here is just gonna be double the height. It might be a little bit more narrow because there's some limitation, but that doesn't really matter anything for the circuitry here. And then, of course, there's no need for batteries. So the power module that's like that is going to be replaced by a power module, something similar to that, which is just a USB power that then communicates, that also sends communication up to the control module. So that's the only thing that's going to change. So these different layers, there's going to be some restrictions other than what we have here. But in principle, it's going to be the same core and same sensors that can be used. And then, of course, not this module here. So this exercise we do with this NASA HAB is leading straight into to using the same technology on the NanoRac's ISS mission. Judy? Questions?
Great, Bjarke. Thank you so much. There are two questions in the chat, and that is how long will the flight be, and also to what altitude. William, I was wondering, you managed it last year. Can you give us some insight, perhaps, in terms of those questions?
So I was actually looking at documentation to see if there's anything that NASA provides, but I believe the altitude is around 30 to 40,000 feet. And
it's definitely going over 100,000 feet. It's
over 30
yeah,
kilometers. Over 30 kilometers.
Yeah. And I can't remember how long it lasts, but it was a fairly significant time because remember I had to leave. But so I'm going to look through the documentation or look through the data that we had, because I think we had data even though it was all zeros.
Yeah, so what happened with the last mission was that we didn't heat the battery, so we lost power at a certain altitude. That's the reason why I worked hard on making sure this time that we had power. I think that a mission, a typical balloon mission that goes to 100,000 feet is typical something around 2 hours, maybe slightly longer. We have power for 4 hours, and I think, well, 4 hours is everybody using all the power they can possibly use. I expect that we will have power for 10 hours flight. So so that will allow to pull the remote before flight string, let's say an hour before the balloon actually goes off, and then it will fly. I will monitor the flight. So if I don't see any flight, I might not actually turn any circuits on. So it'll be something like, depending on the time from now on to the mission, that I can turn all circuits off and thereby that save power. And then only when we start flying, I can measure that with accelerometer, altimeter, or whatever. I will then turn all the circuits on. They will be turned on first to perform a check to see that they all work, and then they will go off again once that the tests have been completed. So, but we're gonna try to figure out when we get closer what the historical lengths of these flights are. So we have mission data for the entire flight.
Okay, I'll take that as a question to get back to everybody on those parameters.
Right now, I have this SparkFun gas sensor, or BME 688. It's like an environmental sensor, so it does like temperature and pressure, and it also does like some gas sensing or like for sulfur, and so it'll detect like sulfur in the air, I guess. I don't know. We still have to research that a little bit. That's one of my group mates' jobs, but I haven't soldered it yet, but we're also looking maybe into adding a second prototyping chip that will hold like a microphone sensor on there, so we can kind of, I guess, get 2 sets of data at once. So yeah.
Please
Oh,
hold up.
it has GPS and light sensing too capabilities.
Please hold up your microphone if you have it there.
Yes. It's a little. Oh, here, let me take it out. This one's definitely really small. It's a little, it might be a little difficult to add to the prototyping board because of how weird it is, and also like the having 2 sensors at once, but we're looking into it.
So just for everybody else, so this is a I2S, not I2C, but I2S sensor. It's all most digital sound these days run over this, that's called I2S. And the minimum number of pins it needs is 3 pins. So it has what it's called a clock pin, a data pin, and then I have something called word select. Now we don't have those pins on our breakout board. So we do have an I/O pin. So Sabrina can use that one. And then my suggestion is she use the UART, the RX and TX pins also. What that means is if he uses those pins, you have to pull it out when she programs the board. And then once he programs, he can put it back into the board. But now she can't use the serial console to file find what's happening with the sensor, because the sensor using the pins for the serial port for that. So if she wants to kind of like figure out what happens on the board, she needs to actually plug a screen in and then use I2C to send message out to the screen to see what's happened. So I have done a prototype board similar, not a prototype board, but a prototype with a microphone, which is also arriving together with the new side panel here. And that's actually using those exact pins. The interesting thing with a microphone is not necessary to record sounds. That's one thing you can do with it, but you can do a fast Fourier transformation analysis and pick up like frequencies. So if you hear a specific frequency or anything like that, you can use it to measure sound pressure level. So there's a number of different things you can do. Obviously, you want to calibrate it, but one of the things you can do is that you can calibrate it when you come back if you had any success with sound coming out of this thing here. So the way it works is that you kind of like read a buffer and then you write the buffer or analyze the buffer, and you write the analysis to the SD card. That's the best way. Trying to write all the sound to the card is of course not a problem. There's a 32 gigabyte SD card, so it can hold the sound. That's not the problem, but that might take some processing power away because writing to SD card is not the fastest. So analyzing the sound could be interesting. So the programming with a microphone is the tough one. Not putting on a prototype board, even though that's slightly complicated because there's not one row of of connections. There's 2 rows, but the prototype board can handle it. So I'm sure Bridget will figure it out too. Okay.
All right. Well, on our side in Cote d'Ivoire, we haven't worked with the board for a while. So we decided to test our sensors last Saturday. So we tested them. They work fine, all of them. I send some the Kibana pictures to Judy. So we put them on Kibana. So we are waiting for the gas sensor now to test them and then proceed. And also we have received the research subject topics that we will try to pick some of them and then assign to our students so they can try to verify some of the theory in the atmosphere. So that's what we are doing now. So we are waiting for the gas sensors to put them. Now my question is how many sensors we can put on the board? How many sensors maximum can we have?
So you can have 6 sensors on the board. So you can see here, this is the backside
Yes.
on the front here. So you have your extended core here.
Yes.
And you have 6 sensors. So you can have 2 rows of 3 sensors here. So you have a total of 6.
Okay.
And that, of course, if these I have here are like standard sensors. So this is CO2 sensors. This is accelerometer. This is a barometer. This is a weather sensor. This is just a blank little commercial here. And this is a GPS. But you can have, of course, you do a prototype board like this thing here. So what Bridget have done and I have here in my hand is that you can go to Spark from Adafruit and you can actually go to Amazon and buy them. It's a little bit easier with shipping when it comes to these kind of things. So you have these board, but you do have another option, and that is that you have a port here. So if I demonstrate that with this here, with this one here, then there is like another prototype. So there's this very, very, very simple prototype that's meant for schools where they don't want to do anything advanced. They just want to solder a little bit or solder a little bit, as I would say. So this is kind of like a little board, and that can be plugged into this port here. And that you can do on top of the 6 other sensors. So this specific one here is you can put any kind of resistors in. So this is a light dependent resistor, LDR. And then of course, a resistor here as a voltage divider. So these are true hole stuff that you just solder in yourself. So you get like an empty board like that, and then you can put that in. And then you use the onboard ADC. There's an ADC on this thing, analog digital converter, to read out this thing here. And you can, of course, calibrate that against a known value. So this is just for schools where you just want to try something, you want to solder something, you want to kind of like prove you put something up there that you did yourself. It's not like super advanced. And if you can use other resistors, you can have a temperature dependent resistor instead of a light dependent resistor, and all kind of other resistors that are dependent on environmental stuff. Okay, so this is the one thing. There is also a prototype board like the other one. So the prototype board I showed before was like that. They look very much the same. This one here goes into this board here, into this slot here. So so this go in here, and that allows you to put a prototype in here. And I have a version here where I put a prototype on. So here's another little board that I got from SparkFun or Adafruit or one of these guys. and I soldered it in, and there's a configuration here on the back. It's a little bit different from the other one, and you can plug that in. And when you do the microphone, Bridget, I was actually thinking, use this port instead. Because if you use that port instead, you are not using your cell port. So you can actually put it into this board instead. So Jim, on this board here, there is a couple of pins available. So there is, so if I hold this up here, you can see there is there's 2 I/O pins here. So there's 3 I/O pins, and I don't think any of them are being used. These 3 I/O pins are being used by the SD card. If you use SPI down here, you can't use the SD card, so don't touch those ones. But the other 3 pins you might be able to use for the microphone, and then you can still use the serial port to for debugging and things like that. So it might be a good idea to put it on here. And this one here, while the old one, you will do the wires across the short hole here. Here you put in your board on the top line and you make long wires across here. So just a little bit different on this one here. So you can put as I mentioned, your microphone, but of course you can take any other sensor in here. So in reality, if I take this thing here, you have 6 sensors here, plus you can add 1 to the board here. And then finally, there is also, if you are really okay with what you want to do, you can skip all these and you can put 1 big prototype board in. Judy, I think you have one lying. So you can put this prototype board in, which is just kind of like a breadboard style board, where you can plow all your different sensors in, and then you kind of like configure your board yourself. I think just is a text on that side. That probably is. I just can't see it, but there's text on a board that will similar to, yeah, there is text there on a side. So that will give you that will give you an idea about how to put stuff together. But it works very similar to a normal breadboard. You just of course have to solder the stuff. You can't just stick it into these holes. So that is that is what you can do. There's one more thing, is that if you need a lot of data, so if you have, for example, you have 32 gigabyte, which is a maximum, even you can get bigger SD cards like 64, 128, you cannot put a bigger SD card in than 32. It's just the way it's locked down by Arduino. But what you can do is that you can put another SD card in. We have this little SD card holder here. So you can put another SD card in, so you have 64 on 2 drives, if I can call it and use that analogy. So that's
Bjarke, yeah, sorry, Bjarke, we didn't ship that additional SD card board, so it's going to be impossible for people to test their code if it's working, writing to one SD card then to the other. We didn't ship that one. And then there's another aspect I want to raise, and that is we have a physical mechanical constraint in terms of the height of each board. So I'm a little bit concerned if with Bridget's microphone, it looked actually quite thick, that microphone. If you put it onto this board and then put it into that 20-pin connection slot, is she going to run out of physical space?
Yeah, that's a good
between payloads.
Yeah. So Bridget and Jim, just make sure you are staying within 8 millimeter from the surface of your PCB so maybe I can demonstrate it here. So between the boards here, this standoff is 8 millimeter. So you have 8 millimeter before you hit the next PCB, okay? And of course, there's nothing on the bottom of the next PCB, so there's nothing here. So you have the full 8 millimeter. However, I just want to maybe also mention that depending on how you put it together, this port here is fully reversible. So this, I'm just going to demonstrate with this sense. I can put it in like I did before, but I can also turn it upside down and plug it in, and it will still work. So, but you can see here, like with these, sorry, I have to point to the camera. You can see here that it's squeezed a little bit here, so it's bent slightly up because of the true hole thing. And if I was gonna take this one here, then I will definitely get into a problem. I don't even think I can. You can see here that sandwich is like too much, okay? So the thing is that just kind of like try to calculate when you put it in, that if you are actually solder that in that microphone in, that you actually don't want to have the long pins here sticking out and things like that. You know, this construction I have here. So I'm just gonna measure this thing here is 1 point. If I don't take the holes, it's 2 millimeter too high. So this is 11.8, and I'm measuring including the 1.6 for the PCB, okay? But I have this standoff built in here to these holes, so I could probably shave something of that off. So if you take the microphone, if you take and do the wiring, put electric tape on, and then put the microphone as close as you can, then it will probably work. However, just remember the microphone, the hole is on the bottom side, okay? So Bridget, when you look at the microphone, the components on the one side, but the sound comes in from the other side. Just look at your microphone there. And then, so you can see there's a little hole on the opposite side of the components. Yeah, so you can see that's that hole, exactly. That hole that sits there in the middle, that's where the sound comes in. So you can't cover that by having it too close to, you know, the bottom. So you have to put it like with the components facing down, just so you you're aware of that. Okay, but thanks, Judy. That's a good point. I just want to say also, I have this light sensor here. So this is the same light sensor as you guys have already. What I've done is I 3D printed this little mirror thing so I can see it out. Now, this specific one here I did a while ago, like a year ago. I need to redo that because this is 10 millimeter high, and we only have 8 millimeter. So if I was going to use this solution here, I have to cut it down to another 2 millimeter. But you can see here's the sensor in a little mirror here. So not that I think it's super necessary, but I was just experimenting with having stuff facing sideways out of the unit.
Great, Bjarke, thank you. Ifriki, please go ahead.
Hi everybody. Hi Bjarke. Hi William. It's been a while.
Hey. Yeah.
My camera is not working. It gives me all the options except the built-in camera. Why? I'm not sure. Maybe I need to call a priest. Anyway. From my side, some of the team members are connected, and we have sort of pulled the troops back in a few moments, not a few moments, few months ago. So far, what we want to do is to get the basics right in place. What are the basics? Code, soldering. It's no point to solder a dry joint. So we're getting, I am scavenging some old electronics for the team, and then they shall desolder and solder till kingdom come. And at least so that we get some clean solders on the prototypes before we're going to be adding sensors. Then code. Code, we are on this coming from the rocket test. So revisit the code, analyze, dive in, mess with it. But the most interesting part where given the intuition was there wouldn't be so much, there will be quite some constraints on the hardware side, and this workshop is showing that there are quite some constraints on the hardware side. Ordering on Amazon to Douala can be a nightmare, where you have a nightmare. In that nightmare, you're having a nightmare. And we might have to push on the code side, where we will see if we can get on the SD card data insight about the interaction between what the sensors collect as a first step. So raw data insight, which we will analyze on the ground, see if we do a good job, and push it a bit further, the next steps. But here, this is where we are. We want to polish the ability to solder, to actually put new sensors on it in a way that will stand any mechanical shock or things like this. It won't go through all vibration tests, but avoiding dry joints is a good idea on something like this. And get the code to a place where we go a little bit further than just collecting the raw data and storing it on. See if we can take it a bit further. That's the plan.
Excellent. Wonderful. Anybody else wanting to come in and discuss their payloads? Okay, wonderful. So I think that's it for today. And then I'll look. Yes, William, please.
So I did find the information on the altitude and days. I did put it in the chat, but the balloon altitude is actually 120,000 feet. And the time or the duration can go from 2 hours to 3 days, you know, depending upon wind in the atmosphere, but also probably mission, depending on, you know, who needs what, when, in terms of the other payloads on the flight, because we won't be the only one. And all that data actually comes from NASA's website.
Just about 36.5 kilometers.
Say that again.
So it looks like about 36.5 kilometers.
Yeah, I didn't do the conversion.
Yeah, same problem. I'm confused with feet, you're confused with kilometers.
Yeah, okay, here it is.
29.2
to 38.7
yeah,
kilometers.
great.
Yeah.
Okay, well that will be definitely either in the ozone layer or through the ozone layer. So that could be very interesting. Bridget, I wonder if your sensor is going to pick up ozone. I wonder if that's something to look for. Okay, great. Should we call it a day?